Okay, so we're continuing with vectors. We're going to talk a little bit about, um, uh, taking some vectors together and um, uh, finding what's called a resulting measurements, resulting vector. Okay, so we have an example here. Okay, and I want you to imagine. Just take this here. This is something that's nearby, a memory key that's nearby me on the desk. Okay. I want you to imagine that I apply a force in the direction to my right, so I push to the right and it moves to the right. Okay. I want you to also imagine that I put up a direction, a smaller force. Actually, no, I'll go with a bigger force, one upwards. Okay. So upwards, like that. Okay. Now we can see that if I push to the right, it goes to the right. If I push upward, it goes upward. But what happens if I push with both forces together at the same time? Well, then it's going to move up and to the right. Okay? Well, that's really basically the idea of a resultant vector. If I apply two vectors at the same time, okay, or like force or something like that, what is the resulting movement or the resulting force that might happen? Okay, so if I push to the right and I push upward, then I'm pushing up and to the right. Okay, so we have an example here. Suppose I have a force which is called F1. Okay, and F1 is given by I minus 3j plus 4k. Okay, and I have F2, which is 2i plus j minus k. Okay, and these are applied simultaneously. So I have two forces going in different directions, and I want to know what the resulting force is, and I also want to know what the magnitude is. Okay, so what do? I take F1 and F2, and I add them together. Okay, and that is the resulting force. Okay, so that is I minus 3j plus 4k. Okay, and then I'm going to add on 2i plus j minus k, and I want to see where I end up. Okay, so I have 1 plus 2 makes 3 in the I direction. I have minus 3 plus 1 makes minus 2 in the j direction. And I have 4 minus 1 makes plus 3 in the k direction. And if I wanted to write that as a column, it's easy enough to do. It's going to be 3 minus 2 and 3. Okay? And now, how do I find its magnitude? Okay, how do I find its magnitude? Okay. What do I have here? Well, I'm going to have 3 squared because of the 3i. I'm going to have a plus a minus 2 squared because of the j has a minus 2 on it, and I'm going to have plus, and this should have a square on it here, and I'm going to have plus 3 squared. So this is 9 plus 9 plus 4, which is a total of 22. Okay. And then finally, if I just want the original magnitude and not the magnitude squared, then I just take the square root of that 22. Okay, so that's the magnitude and the resultant vector. Okay. I'm going to, oh, by the way, the unit of force is newtons. Okay, so newtons indicate how much force there is. Okay, so this would be in units of newtons. And let's, okay, there's a more complicated thing in the notes here, which I'll talk about. Maybe don't worry about it too much if this seems a bit hard, but we'll talk about it. So this is on page 12. There's an example here. It says a point moves in 2 dimensions, and its movement is described by this. Cos of t times the I vector plus the sine of t times the j vector. So this is still a vector, okay? It has I and j in it, except that instead of being in a fixed position, it changes when t changes, okay? So the first one is a position when t is equal to 0. Okay, which is pretty simple to do. All I do is put the 0 into the function. So I have p then at 0 would be the cos of 0 times I plus the sine of 0 times j. Okay, and you can get this on a calculator, by the way. I've got a calculator nearby if I do. Okay. So the cos of 0 is 1. Okay. So this is equal to 1i. And the sine of 0 is actually 0. And that would be that it's going in the I direction. Okay. We have another one here, which is that the angle here is measured in radians. Okay. We have t equals pi over 2, pi, 3 pi over 4, okay. Well, that's pretty simple. I just put these numbers here in instead of 0. Okay, I'll only do one of them, but let's take pi over 2. Okay, it's pretty simple to do actually. Okay, so if I wanted the first one, I would have that p is the cos of pi over 2 I plus the sine of pi over 2 times j. Okay. The cos of pi over 2, if you put it on a calculator, is 0. And the sine of pi over 2, if you put that into a calculator, is 1. Okay, so that would just be the j vector. Okay, so it points in a different direction as the time changes. Okay, the question is, what is the magnitude of p? Okay. Okay, well, this is going to be the same as before. Okay, this is going to be the cos of t gets squared, and I add the sine of t, which gets squared. And there's a very special thing, which is that for any angle that you might take whatever t is here, okay, if you add cos squared and sine squared together, you always get 1. Okay, always. You may not know that. That doesn't really matter, but it's just something that we can work out. Okay, and that's the square of the magnitude here, which means that the magnitude of the vector is the square root of 1, which is of course 1. Okay. And it says here, describe the motion of the point. I don't really want to get too much into this because I don't really have time. But if I have an xy plane like this, okay, and I have something which moves in this fashion, it's going to move around a circle like this, okay? Okay, so if I wanted to mathematically describe movement around the circle, and this is a circle of length 1, of radius 1, so that length is 1, okay, then this would be the function that describes that movement. Okay, so these are useful things. They're necessary for understanding movement, and they're necessary for understanding, how things behave in the real world, which is, of course, an important thing. Okay, so we'll move on. Okay, and we saw here, and this is very important, okay, I mentioned this at the end of the last video, but it's worth mentioning again, okay, is that if I have two vectors, v1 and v2, and I add them together, I am not in general going to get the sum of the lengths, okay? And the magnitude of the sum is not usually the sum of the lengths, and similarly, if I subtract one from the other, okay, the magnitude of their difference is not the difference in magnitudes, okay? That only happens when things point in the same direction. There's an easy example here. What if I take the length of I plus j? Okay, well then that would be 1 squared plus 1 squared. So the length of I plus j would be the square root of 2. But the length of I is 1, which is the same as the length of j. Okay, and you might think by adding the lengths together I would get 2 because I have two vectors of length 1, but this goes back to the triangle situation that we've talked about here. Okay, so if I go back to the triangle, which I think is here, okay, the length of the vector is less than the sum of the lengths of its components. Okay, that's necessary. Okay, so this side here plus this side is longer than the diagonal. Okay, it's longer than the hypotenuse. There. Okay. The next thing that I have to mention here is the idea of a unit vector. Okay. And a unit vector, a vector, we'll call it V, is a unit vector this is the definition, so I might as well underline it. If its length is 1. Okay, and the I, j, and k vectors are all unit vectors. And while they're unit vectors, they are not the only unit vectors. Okay, so for example, there are a lot of others, and I can actually turn any vector into a unit vector by dividing by its length. Okay, so say I have an example here. Find a unit vector in the direction and I'm going to say here that we'll call this vector W. Okay, so W is the working vector, the one I'm working with. Let's say that that's 3i plus 4j. Okay. And I'm doing this in 2 dimensions just to make the calculations easier, but I could do it in 3 dimensions just fine. It would work exactly the same way. Okay. So the first thing I need here is the length of W. And of course, if I square that, I'm going to get 3 squared plus 4 squared. That's my length formula, but it's also just the Pythagorean theorem. So the length of W here is going to be the square root of 25, which is 5. I'm going to use 3 and 4 a lot when I'm talking about lengths, just because it ends up being a nice easy number. Okay, so the length of this vector is 5. Okay, how can I find a vector in the same direction, which is of length 1? Well, the easy way is just to divide W by 5, or take 1/5 of W. 1/5 of W is a unit vector. Okay, and in general, if I have any vector v and I divide it by its length, okay, this is a unit vector. Provided it's not 0. V is not allowed to be the 0 vector. Okay. Why? Because the 0 vector would have length 0, and then I'm not allowed to divide by 0. So I can always get any unit vector I like. Okay. This is a 3-dimensional example that I'll do next, which is not really any more complicated, but it's just, you know, it's got another term lying around. So this time we're going to let W, our working vector, be 3i plus 4j minus 5k. Okay. So what's the length of W? Well, the length of W squared is just 3 squared plus 4 squared plus minus 5 squared, which is 9 plus 16 plus 25. 9 and 16 makes 25, plus 25 makes 50. So the length of W has to be the square root of 50. Okay, which means that 1 over the square root of 50 times W is a unit vector. So what do I have? 1 over the square root of 50 by 3I plus 4j minus 5k is y. Well, this is a scalar, okay? It's just a number, okay? And it just describes how I stretch or shrink the components, okay? So this is going to give me 3 over the square root of 50 times I plus 4 over the square root of 50 times j. And then I would have minus 5 over the square root of 50 by k. And that's the answer. Okay. This is a perfectly acceptable description of the answer as well. The only difference here is that I haven't multiplied the 1 over the square root of 50 all the way through. The next lecture is going to be on the scalar product, also called the dot product, which is not difficult. It's just kind of a formula you have to remember, but the video would run a little bit long if I started talking about it now, so we're going to wait until the next video to do that. Okay, take care everyone.